Hello, everyone. Good afternoon. It's very nice to see you here. This is Zibo from University of Edinburgh, and I'm a fourth-year PhD student. Today, I'm going to talk about our research collection skeletons, declarative abstractions for data collections, which is under supervision by my supervisors and in collaborations with my colleague from Huawei Research Center. This research has been supported by Huawei Research Center in Edinburgh. So, as we know, data structures are very important in programming, but to pick an appropriate or even an optimal data structure is not an easy task, as there are many choices. If we choose to use concept from abstract data types, it is still very difficult. For example, let us stick with a list structure, but there are many implementation choices. For example, in C++, there are standard template libraries. There are implementations from Boost libraries, and there are implementations from third-party libraries. So it is not a very easy task. And it can be even harder for a programmer to choose a proper data structure, given there are situations where hierarchy exists. For example, in Java collection library or Scala collection library, because data collections there are organized as hierarchies. So, for example, in Java data collection, a stack extends a vector, and the vector implements a list. Especially for a programmer who's new to Java programming, they would question, why would a stack be a vector or a list? Let's consider another simple example. Assume that we'd like to write a piece of code consisting of a loop traversing over data structures, and the data structures contains all of integers, and we'd like to traverse them one by one. For each element, we would like to increase them, increase the element value by 1. So what data collection should we choose? Should we choose a list? Should we choose a vector? Should we choose an array? It's not very straightforward to consider the final answer, but let us consider from another way, from an intuitive way. Let us consider what the properties of the data collections we request. So let us go over the problem domain again. From the very beginning, we'd like to iterate over the elements of the data collections one by one. That means the data collection should be iterable, and we haven't set up any strict rules of the duplication for the elements in the data collection. So that means the data collection can be duplicated. Besides, there isn't any rule about the length or size of the data collection. There isn't any rule about should it be variable or not. That's to say, the data collection can be of variable length, and the data collection should be of ordered distribution in the memory. Then let's write down the collection as the declaration at the bottom of the slides. After the simple motivation examples, let us build the infrastructures of the properties-based programming. In our paper, we have developed collection skeletons, which provides a novel declarative approach to data collections. We have exposed individual properties to be specified, which is very different from that in abstract data types, which are implicit properties. And we identify a set of useful semantic and interface properties which capture the key aspects of data collections that programmers would care about. And I'm going to introduce both groups of properties in the following slides. Finally, we evaluated a prop-typed C++ library implementation of our collection skeletons framework and demonstrates negligible performance impact has been introduced across 3 different hardware platforms. So firstly, let's go over the properties. We propose 8 groups of properties to model our collection skeletons. We distinguish them between semantic properties and interface properties. For semantic properties, they specify the behavior of the collections and methods with which collections are accessed or modified. The first group of semantic properties is uniqueness. It specifies the behavior of the insert function. That's to say, for the insert function, it cannot insert same element more than once. The second group of semantic properties is circularity. It regulates the behavior of the iterator. That is to say, after iterating the last element of the data collection, it should go over to the first one of the data collection. An example is a circular buffer. And for interface properties, they specify certain functionality, usually in forms of access methods to be provided by the collection. The first group is variability, which specifies a function append to add an element to the end of the data collection. There is also a function of delete to decrease the length of the data collection. The second group of interface properties is iterable, which provide a function iter to iterate over every element of the data collection. The third group of interface properties is accessibility, which provides, for example, a bracket operator to access some elements in a data collection based on the index. The fourth group of interface properties is splittability, which provides functions of split it to split data collection into 2 or more parts at some position or at some element. The fifth group of interface properties is unified, which provides function union and find for disjoint sets. There are also some properties that are of hybrid nature. That's to say, they both specify access methods and also change the way operations behave semantically. An example of such a hybrid property is order. The group order, for example, first in, first out, and ordered. For first in, first out, it provides iterator and changes the behavior of the iterator, the first in and first out. Based on the properties, we have implemented a prototyped library with C++ template metaprogramming for collection skeletons. Unlike the hierarchy we mentioned before, we implemented our interface as a flat implementation. In our API, everything is a collection. There's no hierarchy, there's no inheritance. And in this figure, T specifies the elementary data type. It can be integer float or some user-specified types. P1 to Pn are requested properties by the programmers, and F are some optional type parameters that may be used by the programmer. Besides, Based on the programming interface, we have also developed member functions for corresponding interface properties, as we mentioned before, like function append or bracket operator for interface properties. And we have developed default methods for all collections, such as the constructors and getSize function to get the size of the data collection. So as we have already got the interface and we have already know how to declare the data collection based on the properties, the next question should be how to map our declaration to the concrete data structures, because underneath we need the concrete data structures to store our data and to in the lower level order. So we introduced a multi-stage pattern matching algorithm to map the declaration to the optimal data structure implementation. This figure presents the process of the multi-stage pattern matching algorithm. There can be three possible outcomes. The first possible outcome is that properties form eligible declaration and the optimal concrete data structure can be detected. The second possible outcome is the declaration is eligible, but it fails to find concrete data structure because the library hasn't yet support the implementation. The third possible outcome is the declaration is not eligible. For example, if the user misspecified data collection to be ordered and unordered at the same time, this is not an eligible declaration, and this would ultimately lead to a compilation error. So for the multi-staged pattern matching algorithm, the first stage is try to pattern match for the eligible declaration, and the second stage is try to match for the ineligible declaration, and the last phase should be the eligible declaration, but haven't yet support the underneath concrete data structure. Um, in uh, in in this figure, the bold rectangle defines the intermediate class, which is very important for the flexibility of the selection of concrete data structures. As R stores the meta information of the candidate list, for example, there are the possible concrete data structures for the certain properties-based declaration, and function find optimal would operate on intermediate class R to decide the optimal data structure. This process has been now manually hard-coded as we regulated it based on our experience. But in the future research, it can be automated through process as from the paper collection switch of CGO 18. There are also some rules applied to the properties-based library, and as we'd like to make it simple and user-friendly, but some rules are required to prevent non-deterministic behaviors. The first rule is that the property list should be order-free. For example, a collection of properties A and B should be equal to collection of properties B and A. That means the ultimate optimal concrete data structure should be the same, no matter the order. The second rule is that mutually exclusive properties cannot coexist in a property list. As I just mentioned before, a collection which is unordered and ordered should not be exist. And the third rule is that we haven't provided any guarantee at this stage on algebraic operations for properties. For example, if the user wants to merge a collection of property A and a collection of property B, we don't know what's the outcome collection, what the properties should be. We don't know that. But in our future research, this will be investigated. So here goes the evaluation. We have evaluated our prototype library, which is implemented with C++ metaprogramming against standard benchmarks, micro benchmarks, and some open source applications. We have manually rewritten the legacy C benchmarks to replace their low-level data structures with our property-based declaration, as well as their access functions. During this rewritten process, there's no other code rewriting or no optimization of the code itself. Also, we applied same input data for all versions for performance comparison. We have run our programs on 3 different platforms, including Intel desktop, Intel server, and an ARM server. The experimental results are present in these figures. From this figure, we can see most of the benchmarks have better performance than the baseline. However, there are 2 benchmarks that performance worse than the baseline. That's because those benchmarks have their specialized or optimized data structures that after we replaced them with our property-based data collection, the performance could not outperform the original ones. And for most benchmarks, we can confidently say that there is no overhead comparing to the baseline. We also checked the flexibility of our data collections. That is, for some property-based declarations, there can be more than one eligible concrete data structures. So we have checked them by swapping out the concrete data structures without touching the user face codes. And the experimental results show that for benchmark icing and benchmark map, the optimal data structures vary from platforms to platforms. After that, we also checked that some factors such as the size of the input data can have an impact on the performance, and maybe different architectures can have different performance trade-offs. So we picked benchmark by sort and regulate the concrete data structure should be array-based binary tree, and we have found as the increase of the input size data, the speedup may also increase after the input data size has been greater than 512 key. Lastly, I'm going to give some summary and conclusions and our future work. In this research, we have proposed declarative data collections which exposed fundamental collection properties to the programmer. It is quite simplification for the programmer. And according to the experimental results, there's no or minimal performance overhead introduced by our library. And we have provided opportunity for performance improvements through greater implementation flexibility. That is, for one property-based declaration, there can be several concrete data structures, and the concrete data structures can be extended without touching the API of the properties declaration. And we have found different optimal concrete data structures depend on application context and the target platform, which is very interesting. And according to the experimental results, the average speed up across 3 platforms is 2.57 to 2.93, which is also very good. And there can be 3 directions for the future work. The first one is we can port the library to more platforms such as GPUs, and we can investigate the interaction of collection skeletons and parallel algorithms mix skeletons, for example, to apply parallel map or parallel reduce to our properties-based data collections. Thirdly, we'd like to apply machine learning algorithm for concrete data structure selection during runtime, and just like the one mentioned in collection switch. And this is my talk. Many thanks for listening.
Any questions from the audience?
Yeah.
Very cool work. I really enjoyed reading the paper. Thank you very much. Yeah, very cool work. Have you thought, since it doesn't come up in your related or future work section, have you thought of inferring the kind of properties that you need from the usages in a program?
Not yet, because we haven't inferred the properties. We just ask the programmers to use our properties, and we can extend the scope of our properties, but we haven't yet considered how to infer them. Thank you.
Hi, maybe I missed something. So what happens if, which concrete data structure does your system select when there are multiple choices fitting the requirement given by the user?
Currently, for our prototyped library, we choose the optimal data structure based on our practice or our experience. For example, giving declaration, if there can either be STD list or boost container S list, we choose the optimal one based on our practice.
So does your system consider more parameters as well as parameters explicitly given by the user?
No, not yet. And currently, there are only a few parameters we consider. Thank you.
Thank you for your interesting talk. I was wondering, usually when you select a collection implementation, you select them based on performance properties, among other things. So like constant time insertion or being able to be expanded without copying, that sort of stuff. And well, your evaluation included performance numbers, but I didn't see explicit performance properties in your presentations. So I was wondering, could you reflect on that? Would that be a valuable extension, or do you cover that in another way?
Thank you very much. That's a very good question. And that is our future, included in our future work. And those properties, performance-related properties you just mentioned, now we call it non-operational properties for the data collections. There are the time complexity and space complexity as the so-called non-operational properties, and we are going to consider or include in our future prototype library. But at this stage, we only compare the performance before and after our rewritten, but haven't included those properties into the process of selection of the optimal data structures. Thank you.
Okay, let's thank